Okay, here is a lecture for radiation biology, and we are going to be lecturing on the design for radiation protection. Some of the objectives that we have is name the leakage radiation limits for X-ray tubes, list the 9 radiation protection features of radiographic imaging systems, list the 9 radiation protection features for fluoro, and discuss the design of primary and secondary radiation barriers and describe the 3 types of radiation dosimeters used in diagnostic imaging. Now, your Bouchon textbook is really good on this chapter, and I hope you find it interesting. So, a number of features of modern X-ray imaging systems are designed to improve radiographic quality, are also designed to reduce patient dose during X-ray exams. One of the features is SID. Okay, so that's your source to image receptor distance, and it has to have some kind of indicator. So it needs to have either the measurements up on the panel or a measuring tape. I personally like the measuring tape. I can trust them, right? Your SID indicators, so it's laser or measuring tape, must be accurate within 2% of the indicated SID. You're going to do a lab on this so you can measure it out and know how to check for this, okay? These numbers, I put it in red, and I put it in red for a reason. You have to know what the requirements are. So for an SID, it's got to be within 2% of the indicated SID, okay? So it can't be off by more than 2%. The collimation, okay, so your collimator. X-ray beam and light beam must coincide to within 2% of the SID. So your light field and your X-ray field has to be within 2% of the SID. That is another lab that you'll be running to make sure you know how to calculate this also. So as you see, both have to be 2%. So if we're talking about SID, remember 2%, okay? All right, so some other ones that we look at are beam alignment. So each X-ray tube should provide with a mechanism to ensure proper alignment of the X-ray beam and the IR, so the image receptor. So sometimes it can be knocked out of whack with rough handling. So we need to make sure that the beam is aligned. There's also filtration built into the X-ray tubes, so at least 2.5 millimeters of aluminum equivalent when operated above 70 kVp. You should know this by now. We've repeated that a million times, right? So total filtration is added filtration plus the inherent filtration. Remember, in the X-ray tube there's filtration, and in the collimator box there's the added filtration. We also do a test checking the reproducibility of our equipment, okay? So making repeat radiation exposures at the same technique over and over and over, okay? The X-ray intensity should not exceed 5%. So you take an X-ray, let's say 70 at 10, and you get a reading. You take it again, and we have a meter in there measuring, okay? And it reads out, let's say 1 milligray. Then we take another one, and it reads out at 9 milligray. We take another one, it reads out 11 milligray. So it can't exceed 5%, okay, of what is programmed. So we have meters in there, and we check this. So reproducibility is the physics check that is done on all of our equipment yearly. Make sure that it's operating properly. There's another test that we do. It's called linearity. So mass is mass is mass. The maximum acceptable variation in linearity is 10% from one MA station to the adjacent MA station. So what do they mean by MA station? So our MA stations are 25, 50, 100, 125, 150, 200. So you're picking an MA station, and remember, MA times time equals MAS, right? So if we were to jump from a 100 MA station, take an exposure for 10 mass, and then we jump down to a 50 MA station with the reading at 10 mass, it should be within 10% So it shouldn't waver more than 10% between those different MA stations, okay? Operator shield, so the exposure control should be fixed to the operating console and not be a long cord. So you are not allowed to take the exposure switch and go in the x-ray room and make an exposure holding the patient. So that exposure control must be fixed to the console so that you can't be in the room exposing while holding a patient or getting exposed to any type of radiation, okay? So should be able to expose IR while standing in the x-ray suite. Yeah, you can't be in the x-ray room while making an exposure at the same time. All right, so we've got different barriers that we use. So those were all the tests that we run to make sure our tube is operating properly, okay? Now we're going to look at the protective barriers. So 3 types of radiation must be considered when designing an x-ray room. We have primary useful beam, secondary radiation. So we have primary beam, that's what's coming out of the x-ray tube. We have secondary radiation is what is scattered, right? So it's what is changed direction. And we have leakage radiation, and the leakage radiation is what is coming out of the x-ray tube, okay? Well, I should say out of the tube in all directions, other than the primary beam, right? All right, so here we have structural shielding guidelines. So a primary protective barrier, that is a primary protective barrier is where the x-ray beam is directed. So whether it is the wall behind the bucky, right, or the floor when we're shooting standing feet, okay, or under the x-ray table. So those barriers that receive primary beam, okay, need to be 1/16 of an inch of lead and be 7 feet high, okay, so that is a requirement. If it's a secondary barrier, so not receiving the primary beam, but receiving scatter radiation, it is 1/32 of an inch of lead, okay? So it's got to be 1/32 of a lead thickness. Walls in the primary beam will not be directed at, so this is all scatter. Less lead because no radiation directed at those walls. So really important to know that. Now our control booth, okay, where we stand to make those exposure. Radiation must scatter twice before reaching behind the control booth. The lead window of the control booth needs a minimum of 1.5 millimeters of lead equivalent, okay? So they're in red because it's important. All right, primary useful beam, okay? So that's what's coming out of the x-ray tube. Any wall to which the useful beam can be directed is designed as a primary protective barrier. Primary protective barriers can be lined with lead, which we talked about, 1/16 of an inch, or concrete. So 4 inches of concrete equals 1/16 of an inch of lead. So looking here on secondary radiation, we have scatter radiation. The patient is that source of the scatter radiation. Now, could x-rays interact with our carbon fiber table with, other items put in its path? Yes, it could. But typically we say the patient is our primary source of scatter radiation, okay? Leakage radiation is radiation emitted from the x-ray tube housing in all directions other than the useful beam. So remember, the outside of the x-ray tube, right? There's the inside where the x-rays are converted, electrons are converted to photons into x-rays, right? Then we have this lead housing. So the housing is lined with lead, right? Even with it lined with lead, it still has x-ray photons that leak through it, okay? They're too high of energy. So that must be so the radiation coming out of the tube must be less than 1 milligray per hour at 1 meter from the x-ray tube. So don't stand next to a portable machine when you take an x-ray standing by the tube head, because it's telling you that there's photons coming out of that and exposing you, okay? Secondary protective barrier shields, areas from secondary radiation are less thick and do not require lead. All right, so factors that affect barrier thickness. the distance between the X-ray source and the barrier. So we also look at the time of occupancy. So is it a room that's rarely occupied, or are we in there 40 hours a week shooting x-rays, right? Is it just a dedicated chest room, or is it a fluoro room? Okay. So there's full, which is the work areas. There's frequent, which are corridors, restrooms, patient rooms, and occasional, which are waiting rooms, stairways, closets, outside areas. Okay. So if it's in the x-ray room, it's considered a work area, okay? And we do full occupational factors for that. If it's in a hallway or a restroom, it's considered frequent. Occasional is where on the other side here of this wall right here, there would be a hallway. This would be corridor, which would be frequent. If this is a waiting room and there's chairs here, that would be a little bit different. It would be a waiting room, but it's also on a primary barrier wall. Where if it's on the secondary barrier, then it would be occasional. Okay, so they list it as occasional, but you have to be careful with that. So there's a lot of factors that go into this. So they say waiting rooms can be occasional. The thing is, we will not put chairs along this wall. Okay, or else we would bump up to a frequent. We don't want to do that. We want to keep it occasional. And patients are only sitting there, hopefully, for a short period of time. Sometimes we run behind, and the patients will be in there for 2-3 hours. We'd want to move those patients away from this wall. Okay, so we just don't even put chairs there. We will here, though. This is an occasional wall. Okay. All right, so we also look at the workload. So the number of exams and radiation activity in a given room. So more exams in a room require a thicker barrier. We also look at the use factor. So it's the percentage of time the X-ray beam is on, directed towards a particular protective barrier. So we need to look at the workload, right? How much are we doing, and how often are we doing it? Where is it angled? So if it's a chest, dedicated chest room, and this wall would get a ton, right? If it's, 60 exams a day compared to 5 exams a day, that's going to be a huge factor in our workload and our use factor, okay? Also, our KVP. So KVP is the penetrability of the beam, right? So that is also going to affect the barrier thickness. So if you're in a dedicated chest room where you're using 110, 120 KVP, it's going to be very different than you using a podiatry room where you're shooting feet, or podiatric. You're shooting feet all day. So the design of the room is going to be completely different depending on the workload, the use factor, and the KVP. Okay, let's talk about the different ways that we measure the radiation. So measure of radiation intensity is called dosimetry. That's what we use to measure the occupational dose in which you receive, right? So radiation measure devices are used to ensure that you are protected, okay? We use gas-filled detectors and scintillation detectors. So there's a Geiger-Müller detector for nuclear contamination. And there's scintillation detectors that we use in gamma. It's considered a gamma camera, and it's used in nuclear medicine. So we use scintillation cameras when we're doing PET imaging. All right, so there's thermoluminescence dosimeters, so TLDs. It's a personal radiation monitoring badge, right? So there's an emission of light by thermally stimulated crystals, so lithium fluoride, following irradiation. So the intensity of the light is proportional to the dose in which it's receiving, okay? The readout process destroys the stored data, and it can be worn for up to 3 months, which is nice. So just so you guys know, this is a typical radiation badge right here. This is a company, it's called Landauer. You can see the name right there. Very popular company. I'm sure you see these out in the clinical environment. This right here is worn by nuclear medicine techs. It is a ring TLD. And what it does is when the nuclear medicine techs are drawing up all of their radioisotopes, their hands get exposure. So this TLD measures the amount of radiation that their extremities receive. So it's a ring. All right, there's optically stimulated luminescence dosimetry, so OSLDs. So personal radiation monitoring also, it's irradiation of aluminum oxide excites the electrons. During the process, laser light stimulates electrons to return to ground state with the emission of light. So the intensity of the visible light is proportional to the radiation dose in which was received on the badge, okay? This badge can be reanalyzed again and again. So OSLDs are more precise than TLDs, and they can be worn for up to 1 year. Now, typically we don't have you wear them for a year, because if you got a really big dose in January, let's say you're wearing it January to December, we don't know that you received it in January. We don't know when you received that dose. So we take it and we do quarterly. So we do every 3 months so that we can see in a 3-month period of time if you had a high radiation dose level. So knowing these different, the TDL is really important. Knowing the Geiger counter and the scintillation detectors, so gas field detectors, scintillation detectors, really important. So TLDs and OSLDs. Now you'll learn more about these in your second year also. So in summary, we design our X-ray tubes to be safe and to be like the light field and everything else, the MA stations, everything to work properly, and we must test it to ensure that it does, okay? And we also design our rooms based off of how often they're going to be used, what our KVP is, and that way we're sure to put in the proper lead thickness of 1/16 for a primary wall and 1/32 for a secondary wall, or 4 inches of concrete, you know, for our primary walls. So it's really important that we understand how the room is going to be used and what are the hallways, the corridors. Is it a waiting room? What is on the other side of the walls? So radiation can get through those walls through that lead or concrete, okay? So we design the room based on primary protective barriers, secondary barriers, and factors that affect that barrier thickness, okay? And all the different radiation detection and measurements that we talked about. So really important that you guys study this chapter. The red, 2%, different items in there of the measurements is really important that you know so that you'll do well on your quizzes and exams. So good job.